Hi everyone, this is Roger. Last week I gave a talk on 1D diffusion and probability flow and something I called contour lines. At the end of that discussion there was a few questions that came up that we didn't get a chance to answer. So I dived in a little bit more, investigated them, updated the notebook to answer those questions. And unfortunately I'm not going to be around this week. So I was thought I'd just make a recording. We'll either, time permitting, record it or play it during this week's meetup or just post it on the channel. So as a form of just a really quick update, I'll go through a couple slides on the previous talk. Okay, this was the slide that kind of summarized what we were talking about yesterday, or last week rather. So we're talking about diffusion. This is a 1D multi-mode Gaussian distribution for the data. We're adding Gaussian noise to drive it towards a normal distribution, and then doing the reverse time diffusion back into the data distribution. We looked at some stochastic propagation in the forward direction, and then since we're doing, we have a known data distribution, we computed the reverse time score function in closed form, and we were able to plot some of these lines. The question we were trying to answer is, what are these lines exactly? So that was where we started. Okay, and then here was the score function. Again, it's we know that the data distribution, so we can derive this in closed form. And it looks something like this. This is plotting the score function for a few different, in some case unimode, in other cases bimodal Gaussian distributions. So the first one is just I believe it's just a unit norm Gaussian distribution, and the score function is just a linear function crossing through zero. The next one is a sigma 2, so higher variance. You can see that it lowers the slope of the score function, still crossing through zero. And then we start into bimodal. The green one is a bimodal. The points are actually at, I believe it is plus and minus 4. You can see it crosses through zero at those plus and minus 4 points. But in order to have two slopes kind of at that line, there's this connection between the two lines. This is what I was calling a crossover. In the case of balanced bimodal, that crossover goes right through zero. So that's kind of the point in between where the diffusion doesn't know which way do I go. Do I go to the upper or to the lower data mode? And then in an asymmetric weight, so it's still same distribution, normal standard deviation of 1 Gaussian at plus and minus 4, but one is weighted more heavily than the other. That has a shift. The curve doesn't change a lot, but it has a shift. It moves it towards 1. So that crossover point you can see has shifted. And then the purple one, there is no, they're equal weight, but they are different sigma. So in one case, this is the unit norm slope. In the other case, this has I forget the exact value, but it's a less than 1 slope. So it's, the sigma is point something or other, and it has to be much steeper then because of that. So again, these two lines have to be connected. In this case, there's a crossover point, and notice that the crossover point was shifted because of the difference. They're still passing through the plus and minus 4, but the crossover point is shifted towards the node or mode with lower variance. So that'll show up a little later in the talk. We'll see it the data. Okay, so once we have the score function, we can now use this equation to derive the probability flow. So this is going backwards in times towards the data distribution. Given the variance preserving parameters that we used for the forward SDE, combining that with the reverse flow, we get this equation for the probability flows. If we look at those, the unit norm, so this is going, what is the probability flow from time t equals 1000 to times t equals 0? And in the case of and then each of these lines represents a particular point sampled from the prior distribution. In the case of unit norm data, of course, the lines propagate straight across. If you have a biased norm, you can see they go up, etc. If it goes from a low variance to a high variance, you can see it kind of fans out as we get to the data distribution, which would be at time t equals 0. Bimodal, they have this split, and there's this kind of indecision point. This is that middle crossover where it doesn't know, do I go left or right, or up or down, etc. This one was where we had asymmetric variance between the two modes of the Gaussian multimodal data distribution. So it's got this little kink. So the first question was, is that real, or is that like an artifact somehow of implementing it? Is it or numerical something or other that was causing that kink? So that was the first one that came up. Then I want to introduce the other thing we were comparing these probability flows to, which is something I had kind of thrown in. It was initiated by these probability flow lines don't cross over, which means that basically the probability mass between the two contour lines, or the two probability flow lines, has to remain constant. So I looked at it from a CDF, or I think it's cumulative distribution function, which is the integral of the PDF, the probability distribution function, or probability density function, rather. So the blue line's the PDF, the orange line is the CDF, the integral of the blue line, and then I picked some points at like 0.1, 0.2, 0.3, 0.4. So these horizontal lines is the 0.5. Wherever that intersects, and you have to do a solver to find out where that intersects the CDF, because it's not, you can't get it closed form. Then you find out what is the X that would produce that CDF of that value. And then as the PDF varies through time, and we look at these constant probability points on the CDF line, we end up with a contour line, what I call the contour line. And it looks similar to the probability flows that we saw earlier. So the question was, are those contour lines and the probability flow, are they the same? And is it reasonable then to think of probability flow looking at it from kind of this points on the CDF line? And it seemed like, it's not a proof, but it seems like they match up pretty well when we plotted them. But when we went and did the one that had the kink in it, notice that these two diverged. And so the next question was, why are those diverging? And I plotted a little closer in. You could see that there's a lot of variance. Looked at it as a vector field. I didn't get a lot out of that. But one of the suggestions from the group was to look at it from the score function. I think it was Julius that suggested this, and this turned out to be pretty helpful. So I plotted this. So this is, again, the same score function that we saw before. On the right-hand side is the corresponding trajectory lines going forward in time. So I kind of flipped it, going forward in time. So this is probability flow on the right, score function on the left. And the points, colored points, represent lines on that trajectory matching up to the score function. And you can see initially we have a couple points that are below the zero line and one of the points that's above the zero line. And what that means, if you think back to that equation for the gradient of the trajectory, the probability flow, if it's a minus value, that means that the probability flow line could be going up. And if it's a positive value, it means it should be going down. So up here, you get, early on, you get a very it's steep. You're going down a lot because the score function is high. And here you're going up a little because the score function is negative. And I should scroll this back to 0. So you can see that this introduces a pretty sharp spike in the score function. You got your crossover point at 4 and -4, and then, excuse me, your modes are at 4 and -4. That's where the line is 0, score function 0. But there's this crossover that happens in the middle, and you can see it's pretty shifted in this case to the low variance point at +4. And as we go forward in time, we're adding this Gaussian noise to it with a distribution of standard deviation of 1. So that slope, instead of being sharp, that slope is going to have to come down a lot. And so it rapidly comes down. The other one is also, I think, tilting up because I think it was 2, but you don't see it as dramatically. But the interesting thing here is that as this is happening, as this mode is drifting towards a standard deviation of 1, you can see that crossover point right here is shifting. It's shifting towards the center between the two modes. And at one point, this point on the line crosses, it's moved, it has to stay on this score function curve. So it moves from below the line, below 0 to +0. And that represents a point where instead of going up, it turns around and starts going down, moving down over here on the probability flow. So that explains then this kink, and the kink is a real thing, and it appears, it took a while to get there, but it occurs because of that asymmetric variance between the two modes in the bimodal distribution. Somebody had suggested trying to decrease the beta. I think that might have been Janeth, but that actually doesn't prevent the kink. It does slow it down, delays it a little bit, but you can still see those lines were jumping from below the line, below 0 to above 0. So it still has a kink in it. You can also see, I thought that this might be related to the kind of the distance between these 2 points. So I moved it out to 8 and -8. Again, that didn't really change anything. You still had the lines in effect. If I picked the lines earlier, I could have got a better kink if I pulled them over closer. So that didn't change it. The higher variance on the second one, again, notice this point is not as high. It used to be like -40 or something like that. So that you start at a different point, but still you get those lines that get pulled from down below to above, which represents the kink. So that's all normal. So I think, yeah, this explanation, I already kind of jumped the gun and described the explanation of why the kink occurs, and just copied it. So now, so that one kind of explains that. So I don't think it's an error. I think it's the way it works. When you have, it doesn't, not a function of beta, not a function of distance between the points, but rather just a function of having different standard deviation on the two modes. So now I wanted to get back to the question about why is it that there's a deviation between this contour line approach versus probability flow approach. To do that, to kind of arrive at the conclusion for that, I wanted to explain a little bit of how that works. And I'll post the notebook so people can look at the code and see if I've made any mistakes and are also gaining any deeper understanding. But basically, the way I was doing these plots is I was so we wrote a function that using the reparameterization trick, you can solve the mixture of, in closed form, solve the mixture between your original Gaussian multimode distribution and your normal distribution. You compute the weight between the sum of those. It's a weighted sum, and you compute the weights based on t. You add them directly, and so you can jump directly back to a particular time and say what's the CDF at this particular time. I was doing that to pick some points, drive it back to time t equals 1000, and then using now the values of x. So I went from like a CDF probability of 0.6 was the one that was giving us the kink. And I bought back or used this reparameterization to compute exactly the PDF back at the time t equals 1000. And then I plug those into the probability flow equation and do a numerical integration forward back to time, or reverse back to time t equals 0. And that's basically, I believe, is the Euler approximation to integration. And what I thought initially might be more of a numerical instability or something like that. You can maybe define this a little bit that way, but what I started to think is that it was the accumulation of errors during that backward integration that was resulting in some difference in value by the time you got back to t equals 0. And I thought it could still be that it's a numerical instability, but I think it might also just be the Euler approximation to the integral might be introducing a bias, and that might be causing it. So anyhow, that was my suspicion. To test it, I went ahead and instead of going all the way back to t equals 1000, I only go back to t equals 100. And so that allows us to accumulate less error because we're both starting at time t equals 100, and we're just doing the integration back in time from that point. Well, for the probability flow. This is the result that I got from that, and it looks a lot better. So I still see a little bit of drift you can see here. There's a little bit of difference. They're pretty much centered, the green and black. So green is the contour line approach, so the CDF, and black is the probability flow. You can see a little bias, but it's much smaller. So I think that's my conclusion then, is that there is probably the contour line is, in our case, since we know the distribution is exact, is correct. Probability flow is a little bit off. And when you get a probability flow that goes back from t equals 1000 to 100, you accumulate a little error during that time. We're in an area where very small differences in the position here, the x position at time t equals 100, can result in pretty significant trajectories. And so that small accumulated error was showing up as a divergence between the two. Given kind of this drill down, I mean, it's not a proof, but I kind of feel like, yeah, this is a reasonable way to think about it, is these constant value points. The trajectory of these constant value points on the CDF over time is the same as very close to the probability flow line. So anyhow, that's what I got to. I hope that was helpful. Like I said, I'll post this on the Slack channel, and post the notebook on the Slack channel if anybody wants to look any further. Okay, thank you.